Hello, my name is Bill Robbins. Today I'm going to talk about wide bandgap devices. In particular, I'm going to talk about the following topics. The inadequacies of silicon devices for future power electronic applications, and then why, in a qualitative manner, wide bandgap materials will offer improved devices. I'll then do a quantitative comparison to some degree between silicon and wide bandgap devices, and then I'll take a look briefly at what are the existing wide bandgap devices and take a look ahead. Going on to the next slide. Why are silicon devices inadequate for the next generation of devices? I think I went one too far. First, let's look at what the current capabilities of silicon power devices are. This is a three-axis chart, or three-dimensional if you like. On the vertical axis on the left over here, I have the blocking voltage in kilovolts. Along the horizontal axis here, I have the current rating of the device, the on-state current. And then along this axis, sort of coming out of the page if you like, is the switching frequencies. The highest power rated devices are thyristors, but they're also the slowest, and so as you can see they appear in the back of the presentation. GTOs and the related devices, integrated gate commutated thyristors and emitter turnoff thyristors, also are fairly slow, though somewhat faster than the thyristors, and they have fairly high voltage and high current capabilities. Next we see IGBTs, which encompass a very wide range of capabilities, up to several kilovolts, as I'm showing here, and capable of fairly large currents on the order of a couple thousand amps, and switching frequencies between 10 and 100 kilohertz, depending on the exact IBG you're talking about. And then we have MOSFETs, which have fairly limited voltage capabilities and current capabilities. However, they have extremely high switching frequency capabilities compared to the other devices. In looking at this chart, we can see that silicon devices have serviced fairly adequately, but they're beginning to show their limitations. And that's the subject of the next slide. Why are silicon devices inadequate? Basically, the silicon power technology is considered by many people to be fairly mature. We can probably expect only evolutionary improvements in the future. Unipolar silicon devices, MOSFETs, Schottky diodes, are used for high frequencies up to hundreds of kilohertz and even megahertz, and voltages to 1,000 volts. But to go higher, you have to use bipolar devices. Those include SCRs, IGBTs, PIN diodes, field control thyristors, and they are used in the range of 1 to perhaps 20 kilovolts, but with lower switching frequencies, well under 100 kilohertz in most cases. Furthermore, silicon devices are limited to temperatures of 150 to 200 degrees maximum at their junction temperatures. Nowadays, power electronic applications are pushing all of these boundaries to higher voltages, higher operating frequencies, higher temperatures, and overall the converter efficiencies are being increased as much as possible. Silicon device usage in these future applications are going to be difficult and expensive. And so for this reason, people are interested in wide bandgap materials. If we go to the next slide, and never mind the phone ringing in the background, wide bandgap power devices offer many potential solutions. First, these devices are much better than silicon for higher voltage applications. They are faster, they have lower losses, higher operating temperatures. These devices operate by the same physical principles as silicon devices, and their better performance is due to the superior material properties and not new or unique device geometries except in one or two cases. Some of the materials that are of interest today in these wide bandgap materials are gallium arsenide, gallium nitride, and I see I haven't gone to my own slides. The gallium arsenide, gallium nitride, silicon carbide, and diamond. You can read for yourself the qualitative statements that are shown here as to why they are of interest. Particularly gallium nitride and silicon carbide are of interest because they have significantly larger band gaps, which means higher operating temperatures, their thermal conductivities are better, and most importantly, they have much larger breakdown field strength. Of the four materials listed here, diamond is probably the most ideal. It has the largest band gap, the largest breakdown field strength, the largest thermal conductivity, and the mobilities are larger than those in silicon. All of this indicates that these materials potentially are capable of producing superior power devices compared to silicon. We should perhaps, though, take a closer look at these materials in terms of what their properties are. Oops, I'm going too far. This is what I want to look at. Here I have listed several properties in the left-hand column of the materials, and then I've shown silicon, I'm showing gallium arsenide, gallium nitride, silicon carbide, and finally diamond. It's a fairly busy chart. I won't ask you to look at all of these, but in looking at the band gaps as you go across, you can see that the band gaps are significantly larger than silicon except for gallium arsenide. The dielectric constants are similar, though in the last three the dielectric constants are somewhat smaller, particularly in diamond. The saturated electron drift velocities are quite similar. Thermal conductivities, though, however, are significantly different. About 1.5 watts per centimeter per degree centigrade for silicon. Gallium arsenide is poorer, and that argues against its use for power devices. In gallium nitride, it's 2 to 3 times larger. 3 times or more larger in silicon carbide, and in diamond, it's almost 8 or 9 times larger than for silicon. The intrinsic carrier densities are listed here, and in the wide bandgap materials at room temperature, the intrinsic carrier densities look ridiculously small. For example, in diamond, the theoretical estimate is 10 to the minus 23. Well, that's essentially 0 at room temperature. The melting temperature of these materials is listed, and all of them are fairly high. For example, diamond is listed at 4,000 degrees centigrade. This is in the absence of any oxygen in the environment. I have found references which refer to the fact that diamond can burn at 800 degrees centigrade in the presence of oxygen, though one has to have a spark or some source to get it started. Electron mobilities are fairly similar except for gallium arsenide, which is significantly higher. Diamond is better than silicon. Hole mobilities in these materials are somewhat similar, except diamond is probably the best in these materials. The most critical factor is down here at the bottom, the breakdown field strength. As we're going to see as I go through this discussion, the breakdown field strength influences most all of the properties of the devices that we are trying to make. And the fact that gallium nitride, silicon carbide, and diamond have at least an order of magnitude or more larger breakdown field strength than silicon is the main reason that we are interested in these materials, though their high temperature capabilities are also of interest and their larger thermal conductivities. Going on to the next slide, here I am attempting to make a comparison, and I think I may have gone too far. Yeah, between various devices in specific device geometries. In the slide that we're looking at, I'm comparing the blocking voltage parameters for a PN junction, and I'm assuming a step PN junction with some drift region length WD, and I'm assuming a non-punch-through geometry. You can see the pertinent equations that determine the breakdown voltage, the doping density, and the drift region length. And what I've done here is computed for the same breakdown voltage of 1,000 volts. I've computed using the breakdown field strength and the other material parameters what the doping density has to be in each drift region and what the length of that drift region has to be. In silicon, we're talking about 6 times 10 to the 14th donors. We're talking about 67 microns for the drift region length. As we go to the wider bandgap materials, the drift region length gets smaller and smaller, particularly if you notice diamond. The drift region length is only about 2 times 2 microns compared to 67 for silicon. In diamond, we have the doping density up in the 10 to the 17th range compared to 10 to the 14th for the silicon. And the other materials, gallium nitride is similar to diamond in the doping density, and a little bit less than the gallium nitride and diamond is silicon carbide. But they're all much smaller drift region lengths and much higher doping densities than the silicon device. So this indicates, I think, rather conclusively why we are interested in these wide bandgap materials. But we can go on and refine our our comparisons even more. The next slide looks at the on-state resistance in unipolar devices. Here I have a equation which says that the on-state resistance times the area, the so-called specific resistance, given in terms of a breakdown voltage rating and the breakdown field strength and a couple of the device parameters, the dielectric constant and the mobility. I see I have to change my notes. E is should have been epsilon, the dielectric constant. I've normalized these equations to those of silicon and then compared the specific on-state resistance ratio for the other materials. For silicon, it normalizes, of course, to 1. For gallium arsenide, it's about 6% of what the silicon is. For silicon carbide, it's on the order of 10 to the minus 3. For gallium nitride, the ratio is 4 times 10 to the minus 4, and diamond is the best at about 4 times 10 to the minus 5. Obviously, the principal reason for the significant difference when we assume the same breakdown voltage rating is the difference in the breakdown field strength, because that ratio goes as 1 over the breakdown field strength, the quantity cubed. And that's why I made the statement earlier that it's the breakdown field strength of the material that's probably the most important parameter. And then the other parameters, somewhat less important in our consideration, but of practical concern when you're making a power device. If I go on and do a similar comparison, for example, for bipolar devices, here I can approximate the specific on-state resistance by the equation that I show up here. In the numerator, we have the breakdown voltage. In the denominator, we have the mobilities, the excess carrier density, the total carrier density. We're assuming that this is a bipolar device, and so the average carrier density is much larger than the background doping density, and then the breakdown field strength. Again, I'm going to normalize this specific resistance ratio to that of silicon. And then in this table down here, we have, again, the gallium arsenide comparison, the silicon carbide, gallium nitride, and diamond. And they progressively the ratio gets smaller and smaller as you go toward diamond. Even in the silicon carbide, you have an specific on-state resistance about a factor of 10 smaller than that of silicon. And when you get to diamond, you have about a factor of 100. So again, indicating why we are interested in these materials. The high temperature capability of these materials is another quantity of interest. And what I've done in this slide is computed the intrinsic carrier density over a range of temperatures. I don't expect you to look at great detail at at the table, but for example, if you look at an operating temperature of, say, 600 degrees centigrade, the intrinsic carrier density of silicon is almost 10 to the 17th, whereas in silicon carbide it's 10 to the 11th. Similarly for gallium nitride, and for diamond it's about 10 to the 8th. And so at the typical doping densities that we used, our intrinsic carrier densities for these wide bandgap materials are well below the typical doping densities even in the lightly doped drift region. Whereas in silicon at this 600 degrees centigrade, We're a couple orders of magnitude higher in intrinsic carrier density at 600 degrees centigrade compared to what a drift region for a high voltage device would be doped at. Even at 200 degrees centigrade, silicon is approaching 10 to the 14th intrinsic carrier density. And so I think that this set of numbers shows you again why we are so interested in using wide bandgap materials. Theoretically, they have much better high temperature capability than silicon. On the other hand, it's probably overly optimistic to expect that we're going to be able to use these devices at some of these elevated temperatures, because we're talking about the limitations fundamentally imposed by the material, but in practice, these temperature limits that we can operate at are going to be probably significantly lower and be controlled by packaging, interconnect, reliability issues, phase changes, thermal stresses, and the like. For example, capacitors that we would use in a converter probably have a much more limited range of temperatures that they can operate at. For example, it's considered right now that electrolytic capacitors probably can't be used much beyond 100 or 120 degrees centigrade. If I look at some of the other questions that we might ask, we could do a switching speed comparison between these devices, at least in an approximate way. Here I'm looking at silicon versus wide bandgap materials in bipolar devices, and what I'm doing here is I am looking at the PIN diode as a vehicle for doing this. I'm showing the average excess carrier density N sub A as a function of position. And when we're operating in the Onstate with a large excess carrier density, we have approximately, as given by the formula right here, an amount of stored charge equal to the charge times N sub A times the volume, which is the drift region length, W sub D times the cross-sectional area. And the on-state resistance is given by the next formula. And if I take the drift region resistance and put it into the equation for the stored charge, I can write that the storage charge can be written in terms of the drift region resistance and some of the other parameters as I've shown here. And if I normalize those quantities, taking a stored charge for the wide bandgap device in the numerator and in the denominator putting in silicon, I wind up with the equation shown in the upper right hand corner. And if I assume that I'm comparing devices, I would assume that they have the same breakdown voltage rating and the same on-state resistance. And to make things simpler, I'm going to also assume they have the same mobilities. In that case, using the fact that I'm assuming a non-punch-through structure so I can characterize the drift region length in terms of the breakdown voltage and the breakdown field strength, I wind up with an expression for the stored charge in the wide bandgap material divided by the stored charge in silicon is equal to the breakdown field strength of silicon divided by the breakdown field strength of the wide bandgap device, the quantity squared. So what that means is that quantity is going to be significantly less than 1 when we are talking about comparing silicon with a wide bandgap. The bottom line is the wide bandgap device will switch much faster than the silicon using the same drive circuit because there's much less stored charge that we have to put in there or take out. And similar reasoning would apply to IGBTs and GTOs. And a corollary to that would be there's probably significantly less reverse recovery current in the same circuit when we have a silicon device being compared against the wide bandgap material because of the much smaller stored charge. If we look at the switching speeds of unipolar devices, to do this I am going to make use of the cross-sectional view of a MOSFET, which I'm showing here on the left-hand side, and in particular I am dividing the capacitance of the structure into the gate source capacitance, which is in this area right here, and the so-called overlap capacitance, which is the capacitance over the from the gate electrode as it overlaps the drain drift region, which is coming up as in this region right here. And the Gate to drain capacitance is principally that overlap capacitance, and it has two components, the oxide capacitance and the depletion layer. Well, perhaps this is a little bit too detailed for a qualitative discussion like I'm talking about here, but if you do follow through the analysis that I'm doing here, I'm going to key principally on what the depletion layer capacitance is doing and the depletion layer charge. And if I go on to the next slide continues this discussion, and it talks about during the growth of either turn off or the removal of the charge turn on of that depletion layer charge. It's a major part of the MOSFET switching characteristic, and that depletion layer charge can be expressed at the maximum amount is the doping density times Q times the volume of the drift region. And the area of the drift region is essentially the area of that overlap, and so we can write that the depletion layer capacitance, charge, can be written as I'm circling this equation right here. And if we take the ratio of the depletion layer charge for the wide band gap divided by the silicon, we get this ratio, which I am showing just below, which involves the square of the ratio of the breakdown field strengths and the on-state resistances. If we assume the same breakdown voltage values and the same mobility values in our comparison devices, we find that the depletion layer charge for the wide band gap is much less than that of silicon. And so that means the wide band gap switching times are going to be considerably less than comparable silicon devices, assuming the same drive circuits. Basically, it's the smaller size of the wide band gap materials due to the large breakdown field strength that gives us the smaller capacitance in the wide band gap devices and thus the faster switching performance. If we were to compare losses in the circuits, whoops, I'm going too far. Conduction losses in bipolar devices are generated mainly in the drift region at high voltage, and so we have the on-state resistance. If we assume identical breakdown voltages and cross-sectional areas and excess carrier densities, the smaller drift region length of the wide bandgap devices means lower losses. Similarly for the switching losses in bipolar devices, let me go to the right here and talk about the conduction losses in unipolar devices. On-state resistance, which we've already looked at, but I'm putting it up here again for purposes of discussion. If we assume the same breakdown voltage and cross-sectional areas, we're going to have smaller drift region lengths in the wide band gap devices and thus lower on-state losses. And the argument is quite similar when we talk about switching losses that we have already discussed. The smaller drift region lengths mean faster switching times and thus lower switching losses in the wide band gap devices compared to silicon devices. Well, I hope that overview of wide bandgap devices and why, at least in a qualitative sense, they are going to be better than silicon has been a useful discussion for you. Let me finish this discussion by talking briefly about what's currently available, what the research devices look like, and then finally consider what the future may hold. Here are some examples of commercially available wide bandgap devices as of 2014 or early 2015 when I'm making this video. For example, normally off MOSFET made in gallium nitride has a breakdown voltage. There's some available at 600 volts, on-state resistance of about 65 millimos, and capable of handling 15 amps of current. These MOSFETs are essentially lateral MOSFETs, probably using a HIMP structure, so-called high electron mobility structure, which is unique to gallium nitride. Another normally off MOSFET made out of silicon carbide is commercially available from Cree and other manufacturers. 1200 volts, 1700 volts. On-state resistances are quite respectable. For example, the 1200 volt has 25 milliohms and 60 amps. The 1700 volts has a 1 ohm and 3 amp capability, though Some now are even better than that. There is a bipolar junction transistor made by Infineon, I think, out of silicon carbide, 1700 volt breakdown, 110 millimos, 16 amps. Normally on JFET at 1200 volts, 80 millimos and 38 amps. Cascode structures of a high voltage silicon carbide JFET in series with a silicon MOSFET. 1200 volts, 70 millimos, 30 amps, and you can see other capabilities as you go down the list. These are certainly impressive numbers, and most of these are discrete single devices. If you put several of these chips in parallel in a package, the capabilities are even larger. For example, there is one example down at the bottom, a half bridge module of silicon MOSFETs, 1200 volt rating, 5 millimos on-state resistance, and 300 amps of current. This is probably 6 or 8 chips packaged in parallel in one package. If you look at the research that's going on in some of the demonstrated research examples, it's even more impressive. Special versions of Schottky diodes at 10,000 volts and 20 amps, PIN diodes at 4,500 volts, 180 amps, GTO at 4,500 volts and 120 amps, a normally off JFET out of gallium nitride, 600 volts, 100 amps, PIN diode in gallium nitride at 2,600 volts and 5 amps. There's even been demonstrated Schottky diodes in diamond at 10,000 volts, though these are very small area devices and not carrying very much current, though their current density is quite high. So this gives you a feeling of the kind of research that's going on in wide bandgap devices at the present time, and in the future some of these devices are going to find commercial applications. To finish this discussion, take a brief look forward and answer the question, what can we expect in the future? I think we've proven the point that wide bandgap materials are fundamentally superior to silicon devices, particularly for high temperatures and higher breakdown ratings. And fundamentally it's due to the fact that they have a factor of 10 or more larger breakdown field strength. And this higher breakdown field strength enables faster switching at lower losses. That larger band gap means higher operating temperatures, and the larger thermal conductivity means capable of handling higher power dissipation. There are a variety of commercial silicon carbide devices available, and as the time goes on, these devices are going to dominate power electronic applications above 1,000 volts. Gallium nitride devices are theoretically somewhat better than silicon carbide, but their present problem is they lack an availability of inexpensive gallium nitride wafers. And until that problem can be solved, we're not going to see very many gallium nitride wafers for high power devices for high power applications. As I've already pointed out, diamond is the best material for power devices, but it's hampered by the lack of large and relatively inexpensive single crystal wafers. And until those wafers are available, we're not going to see any commercial diamond devices. I would guess that it's going to be 10 to 20 years before we're going to see diamond devices commercially available. That's sticking my neck out some, but I recall about early 2000s I was making a set of lecture notes and was talking about the future of silicon carbide, and there I said, right now there aren't too many devices available, but probably within 10 years we're going to see several devices being commercially available. I would like to think that I was rather good at telling the future, but it was even fairly obvious even at that point that silicon carbide was going to be available. And I think it's safe to say, because of the superiority of diamond for power electronic applications, if we can solve the problem of how to make large, inexpensive diamond, single crystal diamond wafers, we're going to see diamond power electronic devices. Thank you for your attention.